Hi Year 12, this is our fourth lesson for the topic of sequences and series. In this lesson we'll look at geometric sequences. This is what we've learnt so far. We've learnt the difference between a sequence and a series. We learnt about sigma notation. Then we learnt the formula for the nth term of an arithmetic sequence and the sum of n terms of an arithmetic series. Okay, geometric sequences. The terms in a geometric sequence or a geometric progression are separated by a common ratio rather than a common difference. So instead of adding or subtracting the same amount each time, we are multiplying. And to find that common ratio, we can do term 2 divided by term 1 or term 3 divided by term 2. This sequence, 1, 2, 4, 8, 16, is geometric. See, 2 divided by 1 is the same as 4 divided by 2 is the same as 8 divided by 4. Now we can use this formula to work out the common ratio, but it's pretty obvious to see that we're multiplying by 2 each time, and that is the common ratio. So let's prove that the following sequence is geometric and then find the next term. So we want to do the second term divided by the first term and prove that's equal to the third term divided by the second term. So 5 divided by 15 is 1/3. And then 1 2/3 divided by 5, well, that's the same as 5/3 divided by 5, which is 5/3 times a fifth, which is 1/3. So because we have a common ratio, then yes, it is geometric. Now to find the next term, we just multiply this one by 1/3. So the fourth term will be 5/3 times 1/3, which is 5/9. Here's another example. Find x and the common ratio of the terms x minus 3, x, and x plus 12 form a geometric sequence. So we're going to do term 2 divided by term 1 and put that equal to term 3 divided by term 2. Cross multiplying, don't forget your brackets. X squared is equal to x plus 12 in brackets multiplied by x minus 3 in brackets. Now let's expand this right-hand side, and we get x squared is equal to x squared plus 9x minus 36. Tidying this up, these two terms will cancel out. 9x minus 36 is equal to 0, and solving the equation, x is equal to 4. So we've found x, we still need to find the common ratio, and that comes from either this or this, because remember this is term 2 divided by term 1. So let's substitute into here. So r will equal x divided by x minus 3, which is equal to 4 over 4 minus 3, which is 4. Now let's look at the nth term of a geometric sequence. So if the first term of a geometric sequence is a and the common ratio is r, then this is the sequence. Here's our first term. Multiply it by r, we get the second term. Multiply it by r again, we get the third term. Hopefully you can see the pattern here. This is the fourth term. So the nth term will be AR to the n minus 1. And there's our formula. So Tn is equal to AR to the power of n minus 1. Here's our first example. Find the seventh term of the geometric progression 54, negative 18, 6, etc. So A is going to be 54. What about R? So we're going to do negative 18 divided by 54, and reduce that down is negative 1/3. Now we can go into the formula. So we want the seventh term. It will be 54 multiplied by negative 1/3, put that in brackets, to the power of 6. And into the calculator, we end up with 2 over 27. Example 2. Which term of the geometric sequence 2, 6, 18, etc. equals 486. So again, we're going to use our formula. We know A is 2, we know R is 6 divided by 2, which is 3, but we don't know N. So substituting in, we get 2 times 3 to the power of n minus 1 is equal to 486. Now, these sorts of questions, finding the value of n with a geometric sequence, are always going to involve logs. So the first thing we need to do before we take logs of both sides is get rid of this 2. So divide both sides by 2. 3 to the n minus 1 is equal to 243. Taking logs of both sides, we get this. Now, it doesn't matter if you do log base 10 or log base e as long as you are consistent. This is our third log law. The n minus 1 can come down the front. Don't forget the brackets. Divide both sides by log 3, we get n minus 1 is equal to log 243 divided by log 3, and this is equal to 5. So solve n minus 1 is equal to 5, we get n is equal to 6. Okay, let's have a go at simultaneous equations with the geometric sequence. The third term of a geometric progression is 8, and the sixth term is -1. Find the first term and the common ratio. So just like we've done with arithmetic sequences, we're going to set up two equations. But of course, we're going to use the nth term of a geometric sequence formula. So third term is equal to 8. That means AR to the n minus 1, n is 3, so AR squared will equal 8. There's our first equation. Here's the second one. The sixth term will equal AR to the power of 5, and it's equal to -1. Now, unlike arithmetic sequences, we can't add or subtract these ones. We have to divide. So I'm going to do this one divided by this one. And this is what we get. AR to the power of 5 divided by AR squared will equal -1 on 8. So we can cancel these A's, and R to the power of 5 divided by R squared is R cubed. The way to get rid of power of 3 is to do the cube root of both sides. So R is equal to the cube root of -1/8, which is -1/2. Now let's substitute back into equation 1. So that was AR squared is equal to 8. So substituting our -1/2 in, don't forget to put it in brackets. -1/2 all squared is 1/4. And so A times 1/4 is equal to 8. Multiply both sides by 4. A is equal to 32. Okay, let's finish with a past HSC question. The zoom function in a software package multiplies the dimensions of an image by 1.2. In an image, the height of a building is 50 millimeters. After the zoom function is applied once, the height of the building in the image is 60 millimeters. After a second application, its height is 72 millimeters. Part 1, calculate the height of the building in the image after the zoom function has been applied 8 times. Give your answer to the nearest millimeter. Now, typically sequences and series questions in the HSC will be worded type problems. So you've got to interpret the language here. Somehow or other, you've got to figure out that this is a geometric sequence. Now, if we have a look at the language, multiplies, it's giving us a clue, by 1.2. And then it actually spells it out for us here. So if we do 50 times 1.2, we get 60, times by 1.2, we get 72. So we're going to use our nth term of a geometric sequence. A is equal to 50. R is equal to 1.2. And we want to know how big it is after it has been applied 8 times. That's n. So into our formula, term 8 will be 50 times 1.2 to the power of 7. We need to give our answer to the nearest millimeter, and that is 179 millimeters. Part 2. The height of the building in the image is required to be more than 400 millimeters. Starting from the original image, what is the least number of times the zoom function must be applied? So again, we've got A is equal to 50 and R is equal to 1.2, but this time we don't know what n is. So using our formula, we're going to get 50 times 1.2 to the n minus 1, and this is going to equal 400. Okay, divide both sides by 50. 1.2 to the power of n minus 1 is equal to 8, and again take logs of both sides. So log of 1.2 to the power of n minus 1 is equal to log 8. Here's our third log law, so bring the n minus 1 down the front and divide both sides by log of 1.2. So n minus 1 equals log 8 divide log 1.2, which is 11.4. Now we want the image to be more than 400 millimeters, so 11 zoom functions is not going to do it. We need to zoom in 12 times. Okay, that's it for this lesson. Our next lesson, which is our last lesson for this topic, is on geometric series.